So let's summarize a few more thoughts from section 3 here, looking at adaptation options and limits, mitigation pathways, sustainable development, and how mitigation and adaptation interact with sustainable development. Because often adaptation has its own goals and strategies and implementation, and mitigation of course has its own options and pathways, and then sustainable development is trying to accomplish certain things. Is there a guarantee that if we do a good job on adaptation and follow safe and proper pathways for mitigation, that also assures sustainable development? Not always so obvious. With increasing warming, adaptation options will become more constrained and less effective. At higher levels of warming, losses and damages will increase, and additional human and natural systems will reach adaptation limits. So certain ecosystems, certain human conditions like vulnerability to health outcomes or crop adaptations, where you can grow what and so on, can reach their limitations. Integrated, cross-cutting, multi-sectoral solutions increase the effectiveness of adaptation. Maladaptation can create lock-ins of vulnerability, exposure and risks, but can be avoided by long-term planning and the implementation of adaptation actions that are flexible, multi-sectoral and inclusive. This is agreed to be understood at a high confidence. So maladaptation is basically where you are adapting to something that's happening now and you don't have a long-term plan, so in a few years that may end up becoming worse in terms of exacerbating vulnerability and exposure, and in the end increasing the risks. Of course, these are all empirical, learn by doing options. You can't always plan for everything. Nonetheless, example, sea level rise will continue for millennia, but how fast and how much depends on future emissions. And sea level rise is a very local thing. We always think about global mean sea level rise increasing at a certain rate and where it will reach, but the dynamics of the ocean and climate is such that there are places where sea levels will drop, are dropping, and there are places where it will increase and is acceleratingly increasing in certain places because of the various dynamical reasons as well. For example, melting of the Greenland glacier reduces the gravitational pull and accelerates the sea level rise from about, let's say, North Carolina to Massachusetts along the east coast of the US. So here we are looking at sea level rise observations and projections 2020 to 2100, 2150, 2300 relative to 1900. What do you do with this projection to 2300 when there are so many uncertainties by 2100 or even 2150? Well, the models can project them, so they are offered here. What decisions can be made other than to worry about future generations is not always so obvious. So here we are going from 1950 to 2100, again looking at various scenarios. This is the global sea level rise in meters relative to 1900, and again global mean sea level, other than the fact that it indicates our overall impact, may not have much practical value other than to motivate adaptation and mitigation, of course. Unavoidable sea level rise will cause losses of coastal ecosystems and ecosystem services, groundwater salination, flooding and damages to coastal infrastructure. This can be chronic high tide flooding and extreme flooding during storms. So as sea level rises, cyclones, tides will begin to amplify storm surge and inundation, which is of course something one has to worry about a lot for vulnerable coastal communities, because the coastal population continues to increase, and one of the adaptation options of course is to move away from the coast, but it's not always easy to convince people to do that. These cascade into risks to livelihoods, settlements, health, well-being, food and water security, and cultural values as well, like living on fishing as a way of livelihood, or other coastal activities that one can imagine. By 2050, 1 billion people exposed. Extreme sea level events that occurred once per century will be 20 to 30 times more frequent. So climate change always loads the dice, so certain numbers keep getting thrown more often than before, so return periods will keep getting shorter for some of these things, like extreme sea level events. So observed sea level is down here. This is in meters, so we are at about quarter of a meter or so. And sea level rise by 2100 depends on the emission scenarios. So you have very high, intermediate, low, and very low sea level rise. Even that one is about 50 centimeters by 2100. We'll look at 2020 in the next slide. In the meantime, if you look at 2150 and 2300, sea level rise greater than 15 meter cannot be ruled out with very high emissions by 2300. So here you have low emission scenario range, and this is the very high emission scenario range, and these are the likely ranges of sea level rise for these very high, intermediate, and low ranges. But you can see that the uncertainties are high as well. But one should always remember that these models that are projecting sea level often do not include details like land movements or even glacier melt from land releasing water onto the oceans. The dash line here is the likelihood high impact storyline, including ice sheet instability processes under the very high emissions scenario. So for 2020 here, we are looking at responding to sea level rise requiring long-term planning, typical scales of coastal risk management measures. We are looking here at the scale. Higher greenhouse gas emissions lead to larger and faster sea level rise, demanding earlier and stronger responses and reducing the lifetime of some options. So the later we do these things, some options will become unavailable after some time. So examples of timing of half a meter sea level rise here from 2000 to 2100. So very high here, and this is very low in terms of the scales. So we are looking at ecosystem based adaptation. So can we recover mangroves, restore, protect, and prevent degradation of coastal ecosystems so that they can help act as buffers against storms and so on. So we have here about 15 years. Sediment based protection, again about 15 years. Elevating houses, of course that can go on for some time, so we have timelines of 30 years. And long societal legacies, protect levees, protect barriers, planned relocation. These give us 50 years to 100 years or greater than 100 years. Of course there are limitations to these as well, because the erosion and so on determine how rapidly we have to retreat, or whether we are even capable of moving far enough back from the coastlines, because everybody loves the coastline, everybody loves to live near the beach and so on. So the key here is indicative time for planning and implementation, typical intended lifetime of measures as seen here. Okay, so these are indicative time for planning and implementation, and these are typical intended lifetime of the measures. Mitigation pathways limiting human caused global warming requires net zero anthropogenic CO2 emissions. Pathways consistent with 1.5 degrees C and 2 degrees C carbon budgets imply rapid, deep, and in most cases immediate GHG emission reductions in all sectors, which we can say with high confidence. In that sense, we are already behind, because these things should have already started as of 23 March, end of March. We are not there yet. Exceeding a warming level and returning, i.e. overshoot, implies increased risks and potential irreversible impacts. Achieving and sustaining global net negative CO2 emissions would reduce warming, which of course we say with high confidence, but net negative emission is a technological promise that has no guarantee of being accomplished. So we are just relying on those as an optimistic scenario for the future. Many irreversible impacts, of course, glacier melts are among the top ones. Ecosystem losses can also be irreversible. Remaining carbon budgets to limit warming to 1.5 degrees C could soon be exhausted, and those for 2 degrees C largely depleted. Again, this is coming from the fact that the warming is linearly proportional to accumulated carbon since 1850, so each additional ton takes out the cap we have from now to 1.5 degrees C or 2 degrees C. Remaining carbon budgets are similar to emissions from use of existing and planned fossil fuel infrastructure without additional abatement. So we are looking here at carbon budgets and emissions. So I've talked about emissions gaps in several contexts. There are many podcasts that you can look at. So here we are looking at cumulative CO2 emissions, gigaton CO2, historical before 2020. So going here from 0,000, 2000, so historical emissions from 1850 to 2019 in terms of what we are accumulating. So remaining carbon budgets since 2020, you have about 500 gigatons going to 1.5 degrees C with a probability of over 50%, and for 2 degrees C with the probability of 83%, of course you get much higher room for emitting more carbon. Remaining carbon budgets for 1.5 degrees C, 2 degrees C and 2 degrees C with 67% instead of 83% will give us even more room. So this line here indicates maximum emissions to stay within 2 degrees C of warming with 83% chance, and this of course is 1.5 degrees C with 50% probability. Okay, 2020 to 2030 CO2 emissions assuming constant at 2019 level. Again, an assumption that has to be looked at carefully as we go forward to 2030. So here we are for 1.5 degrees C. We are butting right up against it already. Lifetime emissions from fossil fuel infrastructure without additional abatement if historical operating patterns are maintained. So existing and planned, we have already crossed for the 2030 limit of the carbon budget, and we are getting very close to 2 degrees C, but of course there are large uncertainty there. Carbon budget always has large uncertainties because there are still missing sinks in terms of when we do the calculations of what is emitted and what is in the atmosphere, ocean, land, and what is not, what is the residual to balance these emissions and sinks. Okay, every ton of CO2 adds to global warming, of course. Cumulative CO2 emissions and warming until 2050. These emissions determine how much warming we will experience, and different emission scenarios and their ranges of warming are shown here for various scenarios. The most benign one being SSP1, so shared socioeconomic pathway 1 -1.9, so that corresponds to how we deal with mitigation, adaptation, sustainability, etc., and the resulting net additional forcing by 2100 is 1.9 watts per meter squared. And then you have SSP1 2.6, which gives us 2 degrees C warming limit, and then you have middle of the road SSP2 4.5, and then higher ones like SSP 3.3-7, SSP 5-8.5 is basically business as usual, where we don't really do much. So looking at warming since 1850, then the range is here up to 3 degrees C. You can see the historical warming. As we said, we have reached already 1.1 degrees C above the 1850 to 1900 limit, and there is the range. When you average global temperatures, there is always uncertainties, and as going into the future you get plumes of the ranges for various scenarios. And I would always like to remind people, and here are the cumulative CO2 emissions since 1850. Once you go beyond 2050 or even 2040, the scenario uncertainties begin to dominate the ranges shown here, and the scenarios are, imaginative storylines that one has to watch carefully, especially if you look at what happened to the global human system because of COVID, or what's happening now because of the Russian invasion of Ukraine, for example, which has had massive perturbation to the energy markets. Global modeled pathways that limit warming to 1.5 degrees C with 50% probability, with no or limited overshoot, reach net zero CO2 emissions around 2050. So overshoot is basically where you cross the 1.5 degrees C limit and then you come back. How long you cross it and how long you stay beyond 1.5 of course, will have all sorts of consequences on glaciers, sea level rise, ecosystems, human health, and such. Total greenhouse gases reach net zero later, because this is only net zero CO2, doesn't include methane, N2O, HFCs, and so on. So looking at gigatons of CO2 equivalent per year, which includes non-CO2 greenhouse gases, while keeping warming to 1.5 degrees C with greater than 50% probability, with no or limited overshoot. So policies in place are giving us the range by 2100 here in terms of emissions. So this greenhouse gases, where we are historically and where we need to go for greenhouse gases to reach net zero no later than CO2. And CO2 historical has to drop, of course, well below the CO2 equivalent, and there is methane as well. Okay, so look at these ranges with the policies we have in place and how we are behind on even updating our policies. While keeping warming below 2 degrees C gives us more room, as we said, so you can see the numbers here. You will get the most benign scenario coming in here at over 10 gigatons CO2 equivalent, whereas here you are at about 5 or so, or sorry, 0. So you will reach net zero later. That's how I should say it. In fact, instead of 2050, you will be reaching it later. So CO2 will reach net zero by 2050, and you will need to draw down the irreducible emissions, and methane will continue, so the greenhouse gases as a whole will not be zero even by 2100, and so on. Here GHGs themselves reach net zero much later than CO2, but by 2100 we are there at net zero. Okay, the timing of net zero for greenhouse gases, not all scenarios reach net zero by 2100, as we said here, and for CO2, of course, we have to hit it by 2050 for the best global warming targets, and you can see here the timing for GHGs and so on. Finally, long-term interactions between adaptation, mitigation, and sustainable development. Mitigation and adaptation can lead to synergies and trade-offs with sustainable development. With high confidence we can say this. Accelerated and equitable mitigation and adaptation bring benefits from avoiding damages from climate change and are critical to achieving sustainable development. We know this with high confidence. Climate resilient development pathways are progressively constrained by every increment of further warming, which is again known with very high confidence. There is rapidly closing window of opportunity to secure a livable and sustainable future for all, which we again say with very high confidence. Okay, so let me leave this here, and then we'll come back and go into section 4, which is the last section. So this is a brief summary, of course, and since we have the detailed podcasts of the draft releases from previous years, 21, 22, I will, sorry, I got cut off there. So since the reports from the previous releases of AR6 are fairly detailed, I have each working group's summary. I will leave these fairly brief here. Okay, so that should conclude this podcast.